So we're going to do some more examples of pancakes. We're going to make stoichiometry even harder. So we know that we have this recipe: a cup of flour, 2 eggs, half a teaspoon of baking powder, produces 5 pancakes. But what would happen if we had 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder? How many pancakes could we produce? Let's work on that on the next slide. So we know that each ingredient could potentially make a different number of pancakes. Okay, so what we're going to start with is our first ingredient. We have 3 cups of flour. We want to know how many pancakes does this make. So what should I do? I should do a unit conversion, right? And cups of flour will go on bottom. And we're going to go into pancakes. We know from the relationship for every 1 cup of flour that we will have 5 pancakes. So cups of flour cancels off, and we are left with 15 pancakes. But that is only for if we have 3 cups of flour. We also have other ingredients, right? We have 10 eggs. So if we have 10 eggs, let's figure out how many pancakes we need. So eggs will go on bottom because we need to get those units to cancel off, and pancakes will go up on top. What is this relationship? For every 2 eggs, we can make 5 pancakes. Eggs cancel off, and we are left with 25 pancakes. Okay, and then we have a third ingredient, and that is 4 teaspoons of baking powder. I'm going to abbreviate it as BP. So now we have to find this relationship between teaspoons of baking powder and pancakes. The recipe says that for every half a teaspoon of baking powder, we're going to need, or it will produce 5 pancakes. If we do the math, that leaves us with 40 pancakes that we can make. So now each ingredient made a different amount of pancakes, but the question is asking how many pancakes could be produced. Well, we have to look at the one that can make the least. We only have 3 cups of flour, so that limits us to how many pancakes we can make. So 15 pancakes would be the most we could make out of the ingredients that we have. So we are limited to 15 pancakes due to the amount of flour. In chemistry terms, we call the 15 pancakes the theoretical yield, because this is the maximum number of pancakes that we can make. The limiting reactant, or also reactant and reagent, these are the same thing. You'll see them interchanged. The limiting reactant is the flour, because the flour limits the amount of pancakes we can make. Now, let's assume that we are making pancakes and let's say you're not a really good cook. So you spill some of the batter, or you burn a pancake, you drop one on the floor, and then some maybe other uncontrollable events happen so that you can only make 11 pancakes. The actual amount of product made in a chemical reaction is called the actual yield. We can determine the efficiency of making pancakes by calculating the percentage of the maximum number of pancakes we actually make. In chemical reactions, we call this the percent yield. Okay, so that's a little bit wordy. This is the equation that we need to use. So in this problem for pancakes, let's figure out our percent yield. Let's see how good we are as chemists or as a baker. So our actual yield is what we actually make. So if you've physically make pancakes, you saw that you can only make 11 pancakes. And we divided by the theoretical yield. The theoretical yield is the maximum amount of pancakes that we could make. And that is 15 because the flour limited us. We multiply it by 100% to get our percent yield. If we do, we get 73%. So, are you a good baker? If you're about 73%, you're kind of an average. Like it's not great, it's not bad, but you're just kind of average in there. If you are like above 90%, you are a really, really good chemist, and people would be dying to have you. But now, take in mind that there are some chemical reactions that have a very, very low amount of yield that you can actually make. So some reactions, they'll only produce like 10%. So it really depends on the chemical reaction you're looking at. Now let's do a complete problem involving stoichiometry. You will probably see something like this on an exam. This is a very, very common type of problem, and you'll also see this on homework. So you're going to get very, very good at stoichiometry. We have our chemical reaction, 2 NH3, 2 ammonias, plus 3 copper 2 oxide produces nitrogen gas plus 3 coppers plus 3 water molecules. The first question is, how many grams of N2 can be made from 9.05 grams of NH3 by reacting with 45.2 grams of copper 2 oxide? Second thing, what is the limiting and excess reactant? Part C, how much of the excess reactant will remain? In part D, if 4.61 grams of N2 are actually made, what is the percent yield? Okay, so there's a lot of questions here that we need to answer, but what we're going to do is we're going to go through each step. So let's just work on part A. The first question is asking how many grams of N2 can be made. So the first thing I'm going to do is just write a little question mark underneath N2, figure out how many grams of that I need. Can be made from 9.05 grams of NH3. So I'll put that underneath NH3 by reacting with 45.2 grams of copper 2 oxide. Okay, remember with our previous pancake example that we had 3 ingredients. Here we only have 2 ingredients. So what I need to do is I need to take one at a time and convert each one into grams of N2. So I'm going to do a roadmap for just one of them. Well, yeah, just for one of them to save some room. The first thing I need to do is convert our grams of NH3 into moles of NH3. What is the second thing I need to do? Convert moles of NH3 into moles of N2. Remember to write both your moles and N2. So here's the second thing. And then the third thing is to convert moles of N2 into grams of N2. So that is just one part of the problem. We also have to do the exact same thing for our 45.2 grams. Okay, so let's work on it. So we started with what we know, 9.05 grams of NH3. And I need to convert this first into moles of NH3. What unit will go on bottom? Grams of NH3, because I need to get, if one's on top, the other one has to go on bottom in order for them to cancel. And the unit on top will be moles of NH3. Okay, so now how do I find this relationship? I have to look at the periodic table. I'm going to add up the mass of nitrogen and the mass of 3 hydrogens. If you do, you will get 17.03 grams of NH3 for every 1 mole of NH3. What unit cancels off? Grams of NH3. Now we're left with moles of NH3. Okay, so we did the first step. Now let's do the second step. What unit will go on bottom? Moles of NH3. What unit will go up on top? Moles of N2. Where do I find this relationship? By the balanced reaction. If I go to the reaction, they don't tell me it's balanced, so I must go through and just make sure it's balanced. It looks like it is because there's numbers out in front. Okay, so I have 2 nitrogens on the left, 2 nitrogens on the right, so that's good. 3 coppers on the left, 3 coppers on the right, so that's good. Hydrogens. How many hydrogens are on the left? 6 on the left because 2 times 3. And also 6 on the right because of 3 times 2. And then the last one we have oxygens. On the left side we have 3 oxygens because 3 times 1. And then on the right we have 3 as well. So it's already balanced, so we're good. Now how many moles of N2 are there? We only have 1. How many moles of NH3 are there? 2. Okay, now what unit cancels off? Moles of NH3. And then we need to do the third unit conversion. What unit goes on bottom? Moles of N2. What unit goes up on top? Grams of N2. And where do I find this relationship? On the periodic table. So for every 1 mole of N2, if you add up the masses, so 2 times the mass of nitrogen, we would get 28.014 grams of N2. Moles of N2 cancel off. And we are left, if we do the math, so in your calculator, you would put the top in parentheses, divided by the bottom in parentheses. You should get 7.44 grams of N2. Okay, remember, this is just one part of the problem. This is only for 9.05 grams of NH3. So we found that with that many grams of NH3, we could get a total of 7.44 grams of N2. Now what we must do is do the same process, only looking at 45.2 grams of copper 2 oxide. So let's do that. So grams of CuO will go on bottom. Moles of CuO will go up on top. And I find this according to the periodic table. If you add up the copper and oxygen, you get a mass of 79.545 for every 1 mole of copper oxide. Grams cancel off and we're left with moles of copper oxide. Do the second conversion. The unit on bottom will be moles of CuO. And what will go up on top? moles of N2, because ultimately we have to convert all of these into nitrogen, moles of nitrogen, or grams of nitrogen. Okay, find this relationship by looking at the balanced reaction. For every 1 mole of nitrogen, there are 3 moles of copper 2 oxide. Moles of copper oxide, or copper 2 oxide, get canceled off. And we do our last unit conversion. For every 1 mole of N2, we have to figure out how many grams of N2 there are. This is according to the periodic table. Add them up, and we actually already did this. We found it to be 28.014 grams of N2. Alright, so we do the math, and we get 5.306 grams of N2. Now the question is asking how many grams of N2 can be made. So how many grams can we actually make? We can actually only make 5.306. The reason why is because we always pick the smaller amount. The copper 2 oxide limits us to how much we can actually make. Now we have to answer the next questions. What is the limiting and excess reactant? Okay, I'm going to abbreviate this as limiting reactant and our excess reactant. Now remember, reactants are found on what side of the equation? These are found on the left side. So only NH3 and CuO are our ones that we can choose from. Now in the previous problem, which one limited us to how much we could actually make? Was that NH3 or CuO? It was CuO, copper 2 oxide. And our excess one, the one that we can make a lot based off of, is our NH3. Okay, and then we're going to throw in a kind of a curveball here and ask how much of the excess reactant will remain. Okay, so we have to figure out how much NH3 will remain. So how many grams of NH3 will remain? Well, we know on the previous problem that if all of the NH3 got converted, that it would be 7.44 grams of N2. But we could actually, or we could theoretically make only 5.306 grams of N2. So if we subtract that, that gives us a difference of 2.13 grams of N2. Now what we need to do is notice how they're asking for our grams of NH3. Here we have grams of N2. So we have to work backwards. We have 2.13 grams of this, and we have to figure out how much of that is left. Okay, so the first thing we're going to do, convert grams into moles of N2. Second thing, convert moles of N2 into moles of NH3. And then finally convert moles of NH3 into grams of NH3. All right, let's do it. So grams of N2 go on bottom, moles of N2 go up on top, and really what you're going to be doing is just you're going to if you want to cheat in a sense, you can look back to what you did in the previous slide, and all of those numbers are coming from that equation. For every 1 mole of N2, we saw that there were 28.014 grams of N2. Second part, moles of N2 go on bottom. Moles of NH3 go up on top. This is coming from the balanced equation. Or you can look back at what you previously did. You saw that there were, for every 2 moles of NH3, there was 1 mole of N2. And then the third step, oh, I should cancel off my units. Moles of NH3 go on bottom. Grams of NH3 go up on top. For every 1 mole, we found there to be 17.03 grams of NH3. Moles cancel off. If we do the math right, we should end up with 2.59 grams of NH3. That will remain unreacted. The last part of this long stoichiometry problem is, if 4.61 grams of N2 are actually made, what is the percent yield? What we need to do is write the equation for percent yield. If we go back in the previous notes, we would find this equation. So we have to find our actual yield. First, what is our actual yield? This number, this is what you actually found in lab. So 4.61 grams of N2 divided by theoretical. This is how much theoretically we could make. How much was this number? Now, what you have to do is you have to go back to the previous slide for part A. We found that there could only be 5.306 grams of N2 that could be possibly made. This is coming from part A. Then we have to multiply it by 100%. Okay, and if we do, we would find that it would be about 86.9%. So they did a pretty nice job. About 87 roughly % is what they got, and that's a fairly good number. Additional problem. I want you to do this complete problem. You don't have enough room to do it on your slides, so I want you to put this on a separate piece of paper. And I want you to answer the following questions, 1 through 4, using the balanced chemical reaction. And then we will check your answer in class.